Thank you. So as I said, the pain of this kidney stone comes and goes, and I may have to stop class at some point. But I thought I'd pass out the copies of Chapter 2, which is something that was easy to do. So, last time we were talking about Hermitian matrices, and we learned that, probably you already knew, that if A is a Hermitian matrix, then A has eigenvectors, and the eigenvectors are orthogonal and if you normalize them, then they're, let's see, that's not a very good way to write now that I think about it, because we kind of like the delta function isn't. So they're orthogonal if they're different. And I also mentioned that if some of the eigenvalues are, well, let me first of all say, it has n eigenvectors and n eigenvalues. If the eigenvalues are all different, we're home free, and the n eigenvectors are all orthogonal, and you can normalize them, so you have an orthonormal basis of n eigenvectors. Sometimes, however, the matrix A can be sufficiently symmetric that there are more than one eigenvector for a given eigenvalue. And we say that that eigenvalue is degenerate. And if there are several of them with the same eigenvalue, and you take any linear combination of them, then this is going to be a sum C alpha AA, which is then the sum C alpha, and there's altogether just one A because it's the same. I'm summing here over the same eigenvalue. Then, in other words, A maps any linear combination of the degenerate eigenvalues eigenvectors corresponding to a particular eigenvalue into a multiple, namely the eigenvalue times the same linear combination of, well, actually that's a sum over alpha. And this would be so these would be so the eigenvalue would be the same, but I would use alpha to label the different eigenvectors that all have the same eigenvalue. So basically the space of degenerate eigenvectors is invariant under the action of the Hermitian matrix, because it just maps it into the same thing because the eigenvalue is the same. Did everybody get a copy of Chapter 2? You came in late or didn't get one?
I can get one after.
Huh? Here, let me just pass it down. And is anybody missing Chapter 1? Okay, now, by the way, I have this irritating habit of saying okay when I think the lecture's okay. The important thing is whether you think the lecture's okay. And so if something's unclear, you know, ask a question. And I'll give you a candy and try to answer the question. I'm going to be a little bit, because of this kidney stone, I'm going to be a little bit more casual about the proofs today. So in the case, in this situation where we have these degenerate eigenvectors or eigenvalues, as I said, two questions arise. One is, are the degenerate eigenvectors linearly independent? And in as much as these, if they are linearly independent, then one can make them orthonormal, but the question is, how should one make them orthonormal? And which orthonormal set is ideal? Well, let me just mention that if U is any unitary operator that commutes with A, then if you take A, U on an eigenvector with, let us say, eigenvalue A and label K, I was using alpha before. Actually, I seem to be using alpha again. All right, if I follow the notation of the book rather than improvise, then it would be this is the same thing as UA K alpha, but these are degenerate eigenvectors, so this is A sub K U of K alpha. And so and for every unitary matrix, you have a different choice of eigenvalues, eigenvectors for this particular matrix. Now, what is the right way to deal with this situation? Well, from the physics point of view, the right way to deal with it is to realize that if A has too much symmetry, then you can add to A a small number, say epsilon, times some matrix B, and the smart thing to do is to make the matrix B be one that has some physical significance in the problem. And for example, if A is a Hamiltonian, B might be angular momentum, or Z components of angular momentum, and so forth. Then the eigenvalues of this operator, let's see how I wrote them down. We would say, I call them K beta of epsilon, and this would be A K beta of epsilon, K beta epsilon. So, and this thing over here, one could say that this is A of epsilon on the state, K beta epsilon. So what one does is one diagonalizes a different matrix, and in that case, the degeneracy is typically broken, or you can arrange for it to be broken. And then what you do is you have a basis for these matrices, and then you take the limit epsilon going to 0, and that gives you a nice choice of eigenvectors of A, and that is a reasonable way of doing it. Let me go back to the other question, though, namely, are the vectors, when you have degenerate eigenvalues, can you still have a complete set of eigenvectors? And the answer to that is yes, and the argument, roughly speaking, is this. You take, suppose we have AK is A sub K, K. So K is an eigenvector of A. And now we take this matrix element, Ka, Y, and this will be A sub K, Ky, because of course the eigenvalues of a Hermitian operator are real. I forgot to repeat that for you. And so since this is true, if this is 0, then so is that. In other words, if Ky, or if Ky is 0, then Kay is also 0. So that tells you that if you have some states that A maps to 0 and you act on them with A, those states are still mapped to 0. Okay, so you can then argue in more or less this way. You say that, well, let me just repeat that. If the vector y is in the space is y perpendicular to k. It's a space of vectors orthogonal to the eigenvector k of a Hermitian operator A. Then the vector ay is also in that same space. That is to say, it's orthogonal to k. And so what you do then is you say, well, this matrix A is an n by n matrix, so it has at least one eigenvector. Then you consider the space. Suppose the eigenvector is 1. Then you consider the space S perp 1, which is the space of vectors that are orthogonal to the state 1. And this is an n-1 dimensional subspace. And, or to put it differently, the matrix A is represented by A sub n-1, which is an n by n-1 by n-1 dimensional matrix. It'll have one eigenvector. And that eigenvector will be orthogonal to this one. And so then you consider the space, what did I call it? Let us say perpendicular to 2. So now you take the subspace of S perp 1 that is orthogonal to the the eigenvector 1, and that's an n-2 by n-2 dimensional matrix. It has at least one eigenvector, and all these eigenvectors are mutually orthogonal. Eventually you wind up with n orthogonal eigenvectors of the matrix A. And so the bottom line is that every Hermitian matrix, n by n Hermitian matrix, has n orthonormal eigenvectors that form a basis for the n-dimensional space on which the Hermitian operator or matrix A acts. A Hermitian matrix is one that's equal to the complex conjugate of its transpose, but you could consider the special case of a real matrix. Well, a real matrix is Hermitian if it's also symmetric, if it's simply symmetric. Okay, I'm going to skip the seesaw mechanism. Tomorrow, I plan to hold class tomorrow, but for the problem session at 5 o'clock, I don't know what's going on with this kidney stone. Anyway, the next topic is normal matrices. And a normal matrix has a very simple definition. It's a matrix that commutes with its adjoint. And by commute, this symbol, this notation was introduced in quantum mechanics back in the 1920s. The square bracket, matrix, comma, another matrix, square bracket, this always means VV dagger minus V dagger V. And if that's 0, then the matrix is said to be normal. Now there are some obvious normal matrices. If the matrix V is Hermitian, then these two terms are the same. So every Hermitian matrix is normal. But it's also true that every unitary matrix is normal, because if V is unitary, then VV dagger is the identity, and V dagger V is also the identity, so you get sigma. So that's what's true of normal matrices. Now, a matrix V that's normal can be diagonalized by a unitary transformation or rather I should say, if a matrix can be diagonalized by a unitary transformation, then it's automatically normal, because when you compute V dagger, what you get is U dagger V diagonal U times the adjoint of that, which is U dagger V diagonal complex conjugate U. And then you do that minus the thing in the opposite direction. In any event, let me just say, I don't feel well, it's 0. The normal matrices have the similar properties to Hermitian matrices. That is to say, an n by n normal matrix has n orthonormal eigenvectors. And one way, there's a cute little way of seeing this. Suppose K is an eigenvector of V. Then that vector is 0, and then what you can say is that the norm of that vector is also 0. Is 0. And this is K V minus VCKI times, sorry, this was a dagger. And then you put a dagger here, actually. And then this is V minus VKI. And this is K. Okay, but because this is normal, this operator commutes with that one. And what I want is a complex conjugate. And certainly the identity commutes with everything. So we can also write this as K V minus VK I times V dagger minus VK star I K equals 0. And so this tells us that V dagger K is equal to VK star K. And if we take the adjoint of that, what we get is KB. Wait a second, what am I doing? Well, we have two relations, actually. We have V dagger K is V star K, and we also have KV is VK K. And so, if M is an eigenvector of V, then KV M is VM KM. And it's also true, using the other relation, that this is VK KM. And so subtracting, what we get is that 0 is equal to VK minus VM KM. So this shows you that two eigenvectors of a normal matrix with different eigenvalues are orthogonal. You can then go through an argument similar to the one that I did, that I sketched for the Hermitian matrices to show that you have n orthonormal eigenvectors. We also have compatible normal matrices. And I tell you, the pain is getting worse. Let me just summarize the compatible. If two matrices commute, if the commutator is 0, they're said to be compatible. Two normal matrices that commute are said to be compatible, and they can be simultaneously diagonalized. I'm just going to skip the proof because, as I said, I'm in some pain here. All right, the singular value decomposition. That's actually important. And I just don't know if I can do it. But the idea is this. Suppose A is an arbitrary matrix. And let us say it's m by n. It's not even square. Then the bottom line here is that you can always write it as U sigma V dagger. This matrix has eigenvectors on the main diagonal, and this may be, it may look like that, or it may look like this, but those matrices, those eigenvalues are non-negative, and these eigenvalues will be non-negative, and all the other matrix elements will be 0. These things are called the singular values. And so the question is, how is it that, why is this the case? Well, the idea here is that A is mapping us from one vector space, I sub n, which has an identity matrix that might look like that, with n of them, and I sub m has another set of eigenvalues, and the diagonal sum of outer products gives you IM. And there are, of course, an infinite number of different bases for the n by n, the n-dimensional vector space, and the same thing for the m-dimensional vector space. And so the trick with the singular value decomposition is to choose bases, to choose the vectors, the basis for n, for in, and for im in a clever way. And if you choose them in a clever way, you get this singular value vector decomposition. And the trick is very simple. It's just that you say A dagger A. Now, even though M is just some arbitrary complex matrix that's not even square, if you take A dagger A, this is Hermitian. So this does have eigenvalues and eigenvectors. E, not epsilon. And so you choose these as the eigenvectors for, you're going to choose these as the eigenvectors that will use to span the space In. And for the other space, what we're going to do is we're going to choose eigenvectors of A dagger A, no, wait a minute, A dagger, and we'll use them as, what do I call them, BK. And maybe I should, what did I call those? Well, let's just call it E, let's just call it FK. So the singular value decomposition comes, you can construct it just by using the eigenvectors of the two Hermitian matrices, A dagger A and A dagger. And I think I'll leave it at that. I urge you to read the rest of this, but as I said, I'm in some pain, and I just want to quit here. We're going to skip Moore-Penrose pseudo-inverses. It's amusing, you should read it. What I will try to say something about is entanglement, because in particular, I think in one of the problem sections I was too sloppy in what I said was an entangled state. So basically, the idea is the direct product of matrices. So suppose A is n by n, and B is maybe m by m. And now you can have a new matrix that's a direct product, and as a matrix it would be WIK would be a sum on J up to n, a sum on L up to m of C I K J L, and those are actually sum on J, sum on L of AIJ, BKL, VJL. So this is how an arbitrary matrix, that is, this matrix is NM by NM, how that acts on a direct product of two matrices. And one of the things to think about is, or to notice, is if you have an arbitrary vector in S cross T, so this is a direct product of these two vector spaces, then this will be a sum psi I k will be a linear combination of I k. And effectively, that's the same thing as sum on ik of ik, inner product of ik with the state psi. Now, here's the thing to keep in mind. This is the general state. It's an arbitrary linear combination of the direct product states I and k. So if this is n by n, then there are n times m terms here. On the other hand, there's something much, much simpler. Namely, you can imagine that you have a particular vector phi in the space S, the n-dimensional space, and you take its direct product with some vector, an arbitrary vector in the space chi, which is m by n, and this turns out to be a sum phi I chi k ik. Here, what I guess I skipped a step here. I'm going to write this as a sum phi I times the state I cross product with the sum on k of chi k. So that looks like this. But here, this is the space spanned by these direct products is a much lower dimension than the direct product of the two vector spaces. So there's then this definition of entangled, and the idea is, well, let me just give you an example. Gamma gamma is 1 over root 2 so this is an entangled state because if you measure an object in this state and it's spin up, if one particle is spin up, the other one has to be spin up, or if the first one is spin down, the second one has to be spin down. So that's the basic idea of entanglement. Another concept is an important thing is a density operator. The density operator is something more general than a state. A state is a vector. A density operator is Hermitian. It's something that has a trace equal to 1, and all of the diagonal elements are non-negative. That's called a density operator. So a density operator is used to represent a quantum mechanical system where we just do not have complete information. Okay, let me now just give you one more thing to chew on, namely the rank of a matrix. 1 It's the number of linearly independent eigenvectors. 2, it's the, rows, not eigenvectors, rows. Second definition, number of linearly independent columns. Third is number non-zero singular values. And 4, it's the number of rows in the biggest square non-singular submatrix. Square non-singular, in other words, the term is non-zero, submatrix. So there are those 4 different definitions. All right, I think I'm going to stop now because, as I said, I'm just in a certain amount of pain, and because of this pain from this kidney stone, I can't lecture normally. So why don't we go and stop?